Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on recurring decimals. So last lesson we looked at converting fractions and decimals. One of the examples we did, we found that 3 over 8 is the same as 0.375. Another one we did, we found that 9 over 20 is the same as 0.45. So fractions and decimals are just different ways to represent the same number or part of a number. So these two decimals, 0.375 and 0.45, they're relatively easy to work with because they are what we call terminating decimals. Now, terminating means ending or stopping. So what's ending or stopping are the numbers after the decimal point. A terminating decimal means the numbers after the decimal point eventually stop. So unfortunately, not all decimals are nice like that. Some decimals never ever stop, and we're going to look at them in a second. But just before we do that, I want to revisit last lesson again. So let's say I have a fraction like 7 over 25. So remember, there were two ways we went through to convert this to a decimal. So the first method, what we wanted to do was we wanted to make the denominator, the bottom number, a power of 10, like 10, 100,000, 10,000 or whatever, okay? So 25 doesn't go into 10, but it does go into 100. So I can times it by 4. Remember, if I times the bottom by 4, I have to times the top by 4. So what I'm doing is finding an equivalent fraction. So 7 over 25 is the same as 7 times 4, which is 28, over 25 times 4, which is 100. 7 over 25 and 28 over 100 are the same thing. But this fraction here is much easier to convert to a decimal because its denominator is a power of 10. And in decimals like this, each column is a different power of 10. So that's pretty easy. It's just 28 hundredths. Or if you like, we have a decimal. It's obviously less than 1. So 100 is the second column after the decimal point, so there should be two numbers after the decimal point. So take these two digits here. 7 over 25 is 0.28, and that is another terminating decimal. But what I wanted to point out is that that method where I make the fraction have a denominator equal to a power of 10, that won't always work. If I want to, say, convert the fraction 2 over 3 into a decimal, I can't use that method. 3 doesn't go into 10, doesn't go into 100. In fact, it doesn't go into any power of 10. So what I have to do is use the other method I taught you last lesson, and that's the short division algorithm. So 2 over 3 means 2 divided by 3, or how many times does 3 go into 2? Because 3 doesn't go into 2 one time, I can write this as 2.00, as many zeros as I want, of course. 2.0000 is the same as 2. So, I go 3. How many times go into 2? 0. Remainder 2. Remember, decimal point has to be above the decimal point. So now I treat this as 20. How many times 3 go into 20? It goes 6 times, remainder 2. 3 into 20, 6 times, remainder 2. 3 into 20, 6 times, remainder 2. And hopefully what you see is there's a pattern. This is just going to go on and on forever. It will never ever stop. I could keep doing these short divisions one after the other forever and ever. So that means that 2 over 3, if I write that as a decimal, the numbers after the decimal point do not stop. They go on forever. So 2 over 3 is equal to 0.66666. The sixes keep going. Now, because we can't, just keep writing sixes all day, that'd be really boring, we can write it a simpler way. So what we do is we write the decimal, but we just put a dot over the number or numbers that go on forever. So this is what we call exact decimal form. So 2 over 3, we read this as 0.6 recurring. The 6 recurs, it goes on forever. That is an example of a non-terminating decimal or a recurring decimal. So a recurring decimal is one where the numbers after the decimal point go on forever. A little technicality, there has to be a pattern to the numbers after the decimal point, because you will see later that there are actually some decimals that are not terminating and not recurring. So for now, numbers after the decimal point go on forever and there's a pattern to them. It is a recurring decimal. So please pause and copy this down if you need it, because I'm going to go to a new slide. So let's look at another example. So let's say I wanted to convert 7/11 to a decimal. Again, I can't use the first method I taught you last lesson because 11 doesn't go into any power of 10. It doesn't go into 10, 100, 1,000, whatever. I have to use the other method, the short division algorithm. So that is saying how many times does 11 go into 7, and I'll just put a whole bunch of zeros. Doesn't really matter how many zeros you need, you just need enough so that you can see the pattern. So 11 goes into 7 0 times, remainder 7. Remember, decimal point above decimal point. So now I treat this as 70. 11 into 70, 6, remainder 4. 11 into 40, 3, remainder 7. 11 into 70, 6, remainder 4. 11 into 40, 3, remainder 7. And hopefully you can see that this process could just go on and on forever. But I can stop because I see the pattern. Every first number after the decimal point is going to be 6. Every second number after the decimal point is going to be 3. So 7/11 is going to be 0.636363, and it goes on again forever. It never stops. The 6s and 3s go on forever. In exact decimal form, I write 0.63. Both the numbers go on forever. So I put a dot above both numbers, okay? I just want to point out that this is different. If I had the number 0.63 and let's say only the 3s went on forever, but the 6s didn't, then I would only put a dot above the 3. Okay, so I want you to note that this here is different from that. And that's all there is to it. So remember, recurring decimals are decimals where the numbers after the decimal point go on forever and there's a pattern to it. And in order to convert fractions to their recurring decimals, we need to use the short division algorithm. I hope you've enjoyed this video. This has been the luckiest maths teacher in the world. Have a great day.